Alright, so here's a problem related to eigenvectors. We're given a matrix A, negative 1, 1, and 1, 3, and the standard basis vectors, E1, which is 1, 0, and E2, which is 0, 1. And our goal is to find a general formula for the matrix to a power n, a to the n, times each of these basis vectors, E1 and E2. Now, it's really complicated to just try to figure out what the matrix to a power is, because that doesn't necessarily seem to follow any patterns. But what we can do is we can take our vectors, E1 and E2, and our goal is to write them in terms of our eigenvectors. So, for example, well, we have a 2 by 2 matrix, so if we're lucky we're going to find two eigenvectors, x1 and x2. So ax1 is going to give me some lambda 1 x1, and ax2 is going to give us some other eigenvalue, lambda 2 times x2. And if we can write our vectors, e1 as some constant times the first and some other constant times the second, then our matrix to a power, a, just any power of our vector, is going to be the same linear combination, except that we have our eigenvalues raised to the same power as the matrix. So we'll have C1 lambda 1 to the n times our first eigenvector plus C2 lambda 2 raised to the n power times our second eigenvector. So the challenge for this particular problem is we need to figure out what these two eigenvalues and eigenvectors are. We need to find out what are the values of C, and once I find those values of C, we know the eigenvalues and eigenvectors, we can just write down our answer. So here's our strategy. Our goal, big goal, is we want to rewrite our vectors E1, which is 1, 0, and E2, which is 0, 1, in terms of our eigenvectors. So we'll have four basic steps. We start by finding our eigenvalues. We need to find out when a minus lambda I, or equivalently lambda I minus a, has a non-trivial null space. So we do that by finding out when the determinant of the matrix equals 0. Once we know our eigenvalues, we're going to look at that same matrix and find the null vectors. Those are the eigenvectors. Once I have my eigenvectors, we're going to solve for the C's to find our linear combinations. And then once we have our linear combinations, we can write down our general formula, as I described on the previous slide. So, step 1, we need to find the eigenvalues. Now in the previous work that I've illustrated, I've usually done a minus lambda I. Today, I want to illustrate how you do lambda I minus a. So lambda I minus a, we're taking the diagonal matrix with lambda, and we're going to subtract our matrix A. Now, the thing that we have to pay attention to is subtraction is going to change the sign of all the terms in our matrix. This is why I usually haven't done it, because when I write down my new matrix, I get lambda plus 1, almost made the mistake, minus 1, minus 1, and lambda minus 3. Now the advantage of this approach is that when I calculate the determinant of this matrix, my lambdas are already in a form that looks familiar to us when we do our algebra. It looks like it's factored. So when I calculate my determinant, sometimes I forget to turn the pen on. Lambda I minus a, we are taking this determinant lambda plus 1, minus 1, lambda minus 3, and I get it in a form that looks a lot more familiar. Let's see, minus 1 times minus 1 is positive 1, and we subtract that. This is in a form that looks maybe a little algebraically more familiar. So we get lambda squared, foil, I'm thinking foil. First outside that's minus 3, inside that's plus 1, minus 2 lambda. And then our last term's negative 3 minus 1 gives me minus 4. That's my polynomial, and I need that to be equal to 0. And so this is the equation that solves, I solve that to find my eigenvalues. Now, unfortunately, that doesn't factor, so I have to use the quadratic formula. So let me write that down. So here I've written down a general polynomial that I might have seen for these 2 by 2 matrices. My leading coefficient's 1 because I'll always have lambda. But imagine now I have lambda squared plus b lambda plus c equals 0, and the solution is given by the quadratic formula, which we have to sing. Lambda equals negative b plus or minus square root b squared minus 4ac, and a is 1. All over 2a, and again, a is 1. So we're going to use that formula for our polynomial. So here we go. Lambda equals negative b plus or minus square root b squared, that's 4, minus 4ac, that's plus 16. All over 2a. Alright, so let's see what we get. That square root is a 20, so I get 2 plus or minus 20. Has a 2 come out, leaving a 5 all over 2. And so I get 2 eigenvalues. Lambda 1 equals 1 plus root 5, and lambda 2 equals 1 minus root 5. And we found our eigenvalues. Well, now that we found our eigenvalues, we need to find the corresponding eigenvectors. So here I've already written down my first eigenvalue, and I need to calculate the eigenvectors. So, again, we start by thinking about our matrix, lambda I minus a. So we're going to take 1 plus root 5, 1 plus root 5 on the diagonal. And we need to subtract our matrix, negative 1, 1, 1, 3. And remember, all of the terms are going to change sign. So we get, let's see, 2 plus root 5, negative 1, negative 1, and then what? 1 plus root 5 minus 3, so I get negative 2 plus root 5. And we're looking for when this matrix has non-trivial null vectors. Oh, by the way, if we were to have done a minus lambda I, all of these terms would have changed sign. That's the only difference. And so we have the same null vectors. So we're wanting to solve this system lambda I minus a times our vector gives a 0 vector. And what we'll do is we need to do a reduced row echelon form of this matrix. Now, here's where this challenge shows up. I have these square roots, and what I need to do is I need to use what are called conjugates. And to remind you of what a conjugate is, I want to remind you of the product that gives me a difference of squares. If I have a plus b and I multiply it by a minus b, the outer and inner terms of expanding that cancel, and I'm left with a squared minus b squared. So if I have a number like 1 plus the square root of 2, and I multiply it by 1 minus the square root of 2, these are called conjugates because they are going to result in a difference of squares. I get 1 squared minus the square root of 2 squared. And the square root of 2 squared gets rid of the square root. So this is a tool that we can use to change terms that have square roots so that they no longer have square roots. And we're going to take advantage of that when doing our row operations. We're going to use the rescale a row by a conjugate. So let's illustrate. We start with our matrix 2 plus root 5, negative 1, negative 1, and negative 2 plus root 5. Alright. And we don't want a square root in that first term. So we're going to multiply that row. Row 1 is going to be changed to row 1 times the conjugate, 2 minus root 5. Okay, so that gives me a new matrix. And when I multiply the first term by its conjugate, I get 4 minus square root of 5 squared, so that's 4 minus 5. And in the second term, I get minus 1 times 2 minus root 5. Let's just leave that alone for a minute. While we're at it, let's change our second row and get rid of that sign. So row 2, it's going to be negative row 2. So that gives me 1 and 2 minus root 5. Now, check out what happened. This is minus 1. And compare now our two rows. They're the same except for the sign. And so if I change row, let me change back to black. If I change row 1 by saying it's row 1 plus row 2, those rows cancel. And while we're at it, let's put row 1 and row 2 back in the other order. And I get a reduced row echelon form of my matrix. And I can now see that I have a free variable. x2 is free. So my equation is x1 plus 2 minus root 5 x2 equals 0. If we say x2 equals t, then x1 is going to be equal to negative 2 minus root 5 t. And so I get my eigenvector belonging to this eigenvalue. I get, let's see if we change the sign, negative 2 plus root 5 and 1, and any scalar multiple of that. So here I'm going to pick t equals 1. So there's one of my eigenvectors. Well, now we'll do the same thing for our second eigenvalue. We have our matrix lambda 2I minus a. We're going to take 1 minus root 5 and add 1. 1 minus root 5, 1 minus root 5, 0, 0, minus negative 1, 1, 1, 3. So our matrix is 2 minus root 5, minus 1, minus 1, negative 2 minus root 5. Okay, well, let's see. What can we do? We're going to change this row so it has positive 1 here. And then we're going to multiply this row by the conjugate of that corner term. So row 1, we're going to multiply by 2 plus root 5. That's the conjugate. And row 2, we're going to change sign. And then while we're at it, let's switch their order. Okay, so an equivalent matrix is 1, 2 plus root 5. When we multiply by 2 plus root 5. The conjugate is going to give me 4 minus 5, so I get minus 1. And here I get negative 1 times that conjugate. Negative 1 times that conjugate. And lo and behold, row 2 plus row 1 gives me a row of zeros. So I can now identify my free variable. And in a similar way as last time, I now know that my eigenvectors all have to have the form negative 2 minus root 5, 1. And if you don't like that negative sign on top, remember we can multiply this by any t. So what if we choose t equals negative 1? Then I get my second eigenvector is going to be 2 plus root 5 minus 1. All right, now we have our two eigenvectors. Okay, so we're at a good point to recap what we've done. First, we found the eigenvalues. And then for each eigenvalue, we found its corresponding eigenvector. And what we're interested in is we want to find out, are there coefficients, c1 times the first eigenvector plus c2 times the second eigenvector, that will give us our two vectors that we're interested in. There's the first vector, and maybe d1x1 plus d2x2, that'll give us our second standard vector. And we want to try to solve those. So the way that we're going to do that is by creating an augmented matrix. So we'll create a matrix with our two eigenvectors as rows. And if I multiply by c1, c2, I should get 1, 0. Now the cool thing about matrix multiplication is if I wrote that wrong. Put my second coefficients in the second column, I should get, as the answer in the second column, the values of my second term. And notice that this is the identity matrix. Now that is actually why I chose the two vectors that I was interested in today. So we're trying to find that. Okay. So how would I solve those? Well, one way is I could do an augmented matrix. Negative 2 plus root 5, 2 plus root 5, 1 minus 1, augmented by the two values I want. And now put the left-hand side in reduced row echelon form. Now, if you're observant, you should have noticed what I'm actually calculating. When I go to reduced row echelon form, we've done this before. What we're going to get is let's call this matrix something. Let's call that S. We're going to be computing S inverse on the other side. And if we did that with reducing the rows, that's one way. Or we could actually use cofactor expansion, not expansion. We could use the adjoint matrix with cofactors and calculate it directly. Well, how would I do the row operations? Well, first I would switch row 1 and row 2. What that is going to do is it's going to take the 1 minus 1 and it's going to put it up in the first row, which is a better spot for that. And then I want to switch. Once I do that, I'd really like to get rid of this having square roots. And so I'm going to multiply by a conjugate there. So that's now row 2. So we're going to change row 2 to negative 2. well, let's see. You can choose conjugates. I was going to say negative 2 minus root 5, but I think a better choice might actually be positive 2 plus square root of 5, which is also a conjugate, but it's changing the sign of the negative 2 as opposed to the square root. So row 2 we're going to change. Alright. Now the thing you have to remember about row operations is we have to do that to the entire row. So let's move the first row up. And then what happens when I multiply by a conjugate? So 2 times negative 2 is negative 4. Square root of 5 and square root of 5 is 1, and the outer and inner terms cancel. So I'm left with 1. And then in the second term I get 2 plus square root of 5 squared. And I'll probably put that in the wrong spot. 2 plus square root of 5 on the first term and 0. So those came from multiplying this part of the row by that conjugate 2 plus square root of 5. Alright, so let's simplify that. 1 and 1, negative 1. So when I square this number with a radical, I'm going to get the 2 squared is 4 plus square root of 5 squared. So that's going to give me 4 plus 5, that's a 9. And then the outer and the inner terms, I get 2 square root of 5, I'll get 4 square roots of 5. And then we're left with now 0, 2 plus square root of 5, 1, and 0. Alright, so that's my new system. And now I want to switch row 2 and subtract row 1. So that will give me 1 minus 1, 0, 1. 0, so 9 minus negative 1 is 10, plus 4 root 5. 2 plus root 5, and 0. Okay. Now again, this conjugate's somewhat problematic. Let's see, what could I do? Multiply by the conjugate, 10 minus 4 root 5, I guess. 10 minus 4 root 5. And so the top row stays the same. Let me save you time. I'm going to work out the math and be right back. Alright, I'm back. So here, when I multiply the 10 plus 4 root 5 times its conjugate, bunch of simplification, I'm left with 20. When I take 2 plus square root of 5 and multiply it by that same conjugate, again there's some cancellation, and I'm left with 2 square roots of 5. Alright, the next step is to make a 1 where the 20 is, so we divide that row by 20. Alright, well, as I was just doing that math, I realized that I had made a mistake earlier. Right here, when I did row 2 minus row 1, I failed to subtract that 1. So let's see what sorts of corrections we need to make. So that is going to change this to be minus 1. Okay, now that I have changed that term, I now need to multiply that row by 10 minus 4 root 5. So this negative 1 is going to turn into, let's fix this, it's going to turn into 10 minus 4 root 5, change its sign, 4 root 5 minus 10. That's our new matrix there. Okay, and then we're going to do divide it by 20. So let's fix this as well. Let's see. 4 root 5 over 20 is root 5 over 5. So root 5 over 5. Minus 10 over 20, so that's minus a half. Okay. Now we're finally in a position where I can add. Final step, row 1 changes to row 1 plus row 2. So we get our final reduced row echelon form. Root 5 over 10. Root 5 over 10. Let's see, when I add these, I get root 5 over 5. 1 minus a half is plus a half. And root 5 over 5 minus a half. Okay. So this is my inverse matrix. And gives me the coefficients that I was interested in. Alright, a couple little algebra things to note. Root 5 over 10 can also be written as by multiplying top and bottom by square root of 5. I get 5 over 10 root 5. In other words, 1 over 2 square roots of 5. So that's one thing. And the second thing I want to note is root 5 over 5 is 1 over root 5. So an alternate form for my inverse matrix that may be convenient is to think of this as 1 over 2 root 5. 1 over 2 root 5. 1 over root 5 minus plus a half, and 1 over root 5 minus a half. Okay. I just wanted to next illustrate the approach of using the adjoint to find the inverse matrix, and then we'll interpret. Okay, so this alternate approach, we again start with our S, the eigenvectors for my columns. We're going to calculate the inverse matrix using the adjoint. Remember that excuse me, we take the determinant of our matrix, we divide the adjoint by the determinant. And where does the adjoint come from? Well, it comes from the cofactor matrix. So the cofactor matrix, or there should be a way, maybe the cofactor matrix of S, is going to be the matrix we get by looking at the minors. So here we have just -1, and we're going to put that in the first entry of the matrix. And we go to the second, and the minor here is 1. The determinant is 1, but the cofactor has to change the sign. So we're going to put -1 in that next term. So we just go through. Again, this is in negative term, so we're going to change the sign of that one. -2 minus root 5. And the last term is in the positive term, so we're going to leave alone. So -2 plus the square root of 5. And the adjoint is found by the transpose of this matrix. So let's see, we still need to find the determinant. The determinant of S we could do let's just do the standard cross to calculate it. So we get negative 2 plus root 5, change its sign, so that's 2 minus root 5. And then we're going to subtract the product the other way, so minus 2 plus root 5, but they're both being subtracted. 2's cancel, and we're left with negative 2 square roots of 5. Okay, so our inverse matrix is 1 over negative 2 square roots of 5. That's the determinant. And then we're going to take our cofactor matrix and we're going to calculate its transpose. So negative 2 minus root 5 minus 2 plus root 5. And so now I'm going to take that constant and divide it into all the terms. So I get in the first column 1 over 2 root 5 for both terms. That should look familiar. We saw that before. And now we're going to take negative 2 divided by negative 2 root 5. That will give me 1 over root 5. And then plus a half. And this last term, 1 over root 5 minus a half. And this is my inverse matrix. So I want to point out that this is S inverse 1, 0, and the second column is S inverse 0, 1. And what this tells me is that 1, 0 is a linear combination of my original eigenvectors. So we have 1 over 2 root 5 times the first eigenvector, which was negative 2 plus root 5, and 1, plus the coefficient 1 over 2 root 5 times this second eigenvector, which is 2 plus root 5, negative 1. And so this is my E1. I can use my eigenvectors now to calculate the original matrix to any power times E1 as the same coefficients, 1 over 2 root 5, times my eigenvalue, so that first eigenvalue is 1 plus root 5, to the nth power times the same eigenvector. Oops, that's not a fraction. 1. And the second eigenvector has an eigenvalue 1 minus root 5. I raise that to the nth power times the original eigenvector. And so this gives me the formula for a to the n E1. If I want to calculate the corresponding value for the second vector E2, let's see what I get. I get a to the n E2. I read off my coefficients. 1 over root 5 plus a half times the first eigenvalue, 1 plus root 5, to the nth times the first eigenvector, negative 2 plus root 5, 1, plus this second coordinate, 1 over root 5 minus a half, times the second eigenvalue, 1 minus root 5 to the nth, times the second eigenvector. And I apologize, I ran out of space there. 2 plus root 5, negative 1. And that's my formula for a to the n E2. And that's how you can use eigenvectors. It also illustrates how we use conjugates when dealing with these radicals.